Good evening, everyone. I hope I'm audible to you. So, on behalf of the Sri Lanka Technology Campus, I would like to welcome you all to the second webinar of the MSc Live webinar series conducted by the Faculty of Postgraduate Studies and Research at Sri Lanka Technology Campus. The topic today is sensing threats to underwater fiber optic cables. So, now I would like to take you through a small video.
Ages, mankind has dreamed of better communication. In the beginning, a gesture got our attention. Developing language took 2 million years. Communicating over long distances required ingenuity. We invented pictograms and hieroglyphics to launch the age of written communication. Being first with information became crucial. Cyrus the Great, father of the Persian Empire, developed a system of couriers. In Greece, carrier pigeons broadcast the results of the Olympics. We sought faster and more reliable messengers. In the 15th century, Gutenberg's printing press created mass communication. Telecommunications emerged with the optical telegraph. The dream of communicating fast and far became real with the electric telegraph. In 1844, Samuel Morse sent a message from Baltimore to Washington, D.C. Alexander Graham Bell patented the telephone in 1876. Marconi established the first transatlantic wireless link, and television soon followed. With computers, man-machine communication took flight. Satellites made links almost instantaneous. In 1971, Ray Tomlinson created email. The cell phone came next. The World Wide Web, invented by Tim Berners-Lee, brought forth tools like Facebook, Skype, and Twitter. Everywhere there are laptops, tablets, and smartphones. We communicate.
Okay, over to you, Achini.
Thank you, Professor. And I would like to apologize from everyone for the initially caused technical error. And to formally begin the session, now I would like to invite Dr. Lakshita Paharagidara, the Dean of the Faculty of Postgraduate Studies and Research, to deliver the welcome note. Over to you, Dr. Lakshita.
Hello, good evening, everyone. And I would like to, on behalf of the Faculty of Postgraduate Studies and Research, and on behalf of Sri Lanka Technology Campus, I would like to welcome Professor Sumudu Edirisinghe. And also, I would like to welcome all the everyone who has joined today. So I'll give a brief introduction to Professor Sumudu Edirisinghe. Professor Sumudu Edirisinghe obtained his bachelor's in engineering in electronic systems engineering from University of Essex in 1997, and in 2001 was awarded a PhD in optical communications by University of Essex for his research work on high-speed dispersion-tolerant transmission systems. Over the next 25 years, he has been working as a research and development and a design engineer for several telecommunication equipment manufacturers in Europe as well as in the United States of America, designing, developing products and testing transmission equipment for fiber optic communication systems. He holds several US patents and has several publications under his name. And he's currently a principal subsea engineer at Nokia. and an adjunct professor at Sri Lanka Technology Campus, as well as at Kotalala Defence University, Sri Lanka. And he's also a lecturer of our Masters of Science in Electronics and Communications Engineering program. So I would like to again welcome Professor Sumudu Edirisinghe, and without taking much time, I would like to hand over this to Professor Edirisinghe. Professor Edirisinghe, over to you.
Thank you, Dr. Lakshita. So let me share my screen. Once again, share sound. Right, thank you, Dr. Lakshita, for that introduction. So we live in a world today that our telecommunication needs are not essential need. I would say that this has become a basic human necessity, just like housing, food, without telecommunications, we are kind of lost in our world, especially at this point of time. And without applications like Google Maps and so on, we might not be able to get from A to B in most of the cases. But you would wonder that most of you might still think that this data that you seek from a data server or a data center somewhere residing outside the world, connecting even this lecture, connecting to you is done through satellites. I was, when I was undergraduate trainee, I worked at the Pardukka satellite station in 1995. And at that time, all the satellite dishes were working, and that place was a lively operational hub connecting Sri Lanka to the rest of the world. But in the course of something like 5 to 10 years from that point, the satellite usage has declined. And today, as most of you have experienced, all the satellites at Pardukka have been switched off. And our communications are not mainly made by satellites. That doesn't mean satellites still not operate. They still provide some communications. And one of the famous ones is SpaceX, where they're now not using radio frequencies, but using lasers to provide communication through satellites. But most of our communications, and in this lecture itself, because I am currently in Baltimore in USA, this lecture comes to you through a web of sub-cables, which are fiber optic cables, which are strewn across land and sea. So and over the last few years, this cable map will show you the amount of fiber optic cables have grown. The first fiber optic cable was between the USA and the UK, done in 1988. And from that point, every year, more and more cables have gone into service. And today, these 5 undersea fiber optic cables are the lifeblood that gets you the services such as Facebook, YouTube, TikTok. All the data information comes through this web of cables. The fiber optic cable manufacturers are working 365 days a year, every day of the week, and their factories, the 4 main suppliers of fiber optic cables, especially the submarine cables, their factory capacity has been booked out for the next 5 years. The world is running out of resources to supply the demand of optical fiber cables that is currently happening. So from the point that I know some of you are using iPads, some of you are connecting through your wireless network at home, some of you are using your mobile phone to connect to this as a webinar. And most of that, the wireless part of that communication lasts for maybe the last few meters in terms of wireless communication or Wi-Fi. If it's a GSM or 5G network, it would be maybe a few kilometers. From the cell tower to the rest of the world, you are connected through a series of optical fibers. So every connection that you see in this screen is done through an optical fiber. Now, I'm not going to concentrate on what's happening in land, because Yes, the cables in the land section do get cut. People do sabotage them. You have rats eating through cables. You have vehicles piling into pylons, breaking the cables. You have excavators digging the floor, cutting out the cables. But repairing and locating a fault in the land is easy. When you cut the cable, when an excavator go through the cable, they know exactly where the problem is, and we can send somebody to resplice and reconnect the cable. But unfortunately, the problem is much significantly larger and more difficult when you are in the sea. So my lecture is going to be focusing on how we detect what are the problems in the sea, or how do these cables get cut. And with the increasing density of cables, increasing number of fiber optic cables going in the sea, is there a way of locating and fixing these cables much quicker than before? But pertinently, most of my work, which I'm going to present at the last part of this lecture, would be actually how we can use subsea cables to provide an additional service or to people who live in a coastal area, such as tsunami warnings and earthquake sensing. A fiber optic cable system that goes under the sea has a few elements. It would have a landing station. For instance, if you're in Sri Lanka, there's 2 landing stations in Browns Hill in Mathura. The cable actually lands in the beach there on Mathura. There's a hand that's holding a globe if you walk on the Mathura beach, and the SMIEEE cable actually comes underneath that statue, and it heads up to the landing station up in Browns Hill. From that point, it connects, if I concentrate on SMIEEE cable, it would connect to one side to Saudi Arabia and the other side to Singapore. The fiber optic cable does not do this without any help. The signal every 50, 60, 70 kilometers will go down, and it needs amplification. So you would need some kind of a repeater or an equalizer to bring the signal up every 50, 60 or 100 kilometers. In addition, you will need some branching units, because sometimes one cable not just connects between one country and another country, it would connect to multiple countries. So for instance, SMIEEE cable actually connects on the way to Saudi Arabia. Part of it drops in India, part of it drops in Pakistan. So we would need some branching units to branch out the cable. In order to provide power or electrical current to energize these repeaters, we need to send electricity through the cable to these amplifiers. And these are done with special power feed equipment. And inside the fiber optic cable, there's a copper tube that actually carries the current. If I zoom into optical fiber cable that sits under the sea, you can see the tiny fragments similar to size of your hair is what is used for the communication. We would have something like 8 or 16 fiber pairs connecting 2 countries. Around it, there are some steel overing to protect the cable, and then there's a copper cylinder that goes around it. That is the one that carries the electricity to energize the cable to provide amplification every 50 or 60 kilometers. Now, beyond that, everything, there's a polycarbonate protection layer, and then there are 2 rings of steel armoring. Then there's Kevlar and tar-induced protection around it. All this is there to protect the cable from damage under the sea. These cables are laid 8,000 meters, and some places like in the Atlantic, the sea is 8 kilometers deep. So this actual fiber optic cable sits on the bottom of the sea floor. When you are laying a cable on the bottom of the sea floor, you would come across rocky areas where the cable will move for the current and it would damage the cable. So to protect against that, we use these extra steel cables in regions where we believe that there could be some hazards. For instance, close to the coast, like in Mathura, you would have fishermen going and putting their anchors or fishing nets and dragging them. And they could pull up the fiber optic cable, and due to the immense tension on the cable, you could break the cable. Now, this has become a significant problem as we rely more and more on these subsea cables as we go along. Now, laying a subsea cable is an expensive procedure. It takes many years of planning. Now, the SMIEEE 6 cable is being laid and is going to connect to Sri Lanka pretty soon, or I think it is already connected. And that has taken something close. The planning for that started in 2018. So it's almost nearly 8 years from the planning stage to delivering the cable. This requires an extensive survey of the subsea, submarine area, and laying cables would take months, one, because of the weather, secondly, because of the permits, different countries and different areas, because if it's a conservation area, if it's a tourist area, if it's a fishing area, those things would take longer to get permits to lay the cable. Ultimately, a fiber optic cable end-to-end would cost millions or if not billions of dollars of investment. These cables are planned for a 25-year lifetime. So once they have installed, we need to make sure that they will be operational for a 25-year period. At the depths that we are talking about 8 kilometers below the sea surface, the pressure on the cable is immense. And also the gases like oxygen and nitrogen that's in the water actually dissolves in the at that pressure into the water, and they become acidic. So they also attack the cable. But over the years, people have developed new techniques to protect against the high pressure and the chemical changes in the water in that depth. Well, however, we still have
canyon, one by one, the cables snap. There are so many ways that the internet can physically break. You can have an earthquake.
Well, let me give me a second, please. Well, so
That canyon, one by one,
stop it.
the cables snap.
Okay. So the first video here shows how sharks can attack cables. So undersea cables do get attacked by sharks. They also get damaged by the underlying conditions. And in this video,
There are so many ways that the internet can physically break. You can have an earthquake. You can have anchors that pass by and pick these cables up and tear them in pieces. Fishing trawlers can do it. And you can even have sabotage. Fixing these cables is really an incredible operation. I mean, you have to have a fleet of repair ships sitting by to find them and fix it. Sometimes they'll send a remotely operated vehicle with a camera down to the bottom of the sea. Once they find a break in the cable, they have to bring that cable back up to the surface, then delicately fuse them back together, drop it back down into the ocean, and make sure that it's still carrying signals.
So one of the problems that we have is the cables, as you say, get damaged by shark attacks, fishing nets, ship anchors. But recently we have seen threats in certain parts of the world where the cables are deliberately targeted by certain groups and terrorist groups such as the Houthis in the Yemen and Djibouti waters, where they deliberately cut the cable for ransom. So not only that they commandeer ships and take people hostage, but they would also take your data as hostage, cutting the cables. Now, this happened in 2024 March. Several cables in this region got cut. And you can see this map that I have got on the screen connecting Egypt to Asia. This is the main gateway where your data connects to the Western world. Any data or any connection you are doing on a Google search on a server in the US or in Europe goes through any of these fiber cables laid in the Red Sea from Egypt through the Red Sea into the Indian Ocean. Now, the Red Sea poses a huge threat to us because there's the location of Djibouti and Yemen. The Gulf of Aden is one of the narrowest international waters in the world. There's only 1 kilometer of international water in the world. And to make matters worse, Yemen doesn't have a government. It's run by Houthi rebels. Djibouti have a very fractional government. And then on the tip, you have the Somali pirates on the tip of that entrance to the Red Sea. On the other side, you have Sudan, which is having civil war. Further up in the Gulf, closer to Egypt, you have the current wars between Israel and the Palestine. So all these politically unrest parts of the world is in this very precious commodity that we need to lay these cables. So finding a repair and making a cable repair costs, again, hundreds of thousands of dollars. In every ocean, we keep a repair ship. And to keep a repair ship afloat, it costs $100,000 per day. We have to pay the ship, the expenses and the crew, even if they're not repairing something, $100,000 per day. If a cable gets cut, we have to book one of these ships. These ships need to come into the country to pick up the spare parts that is needed.
The Fukushima nuclear accident occurred on March 11, 2011, after a massive earthquake and tsunami hit Japan. The earthquake, a magnitude 9.0, was one of the most powerful ever recorded. The tsunami that followed flooded the Fukushima Daiichi nuclear power plant, knocking out its power supply and disabling the cooling systems for its nuclear reactors. Without proper cooling, the reactors overheated, leading to nuclear meltdowns in 3 of them over the following days. This caused several explosions due to the buildup of hydrogen gas, releasing radioactive material into the atmosphere. The accident forced the evacuation of more than 150,000 people from the surrounding area due to fears of radiation exposure. The Fukushima disaster is considered the worst nuclear accident since Chernobyl in 1986. Although no deaths have been directly attributed to radiation exposure, the long-term health effects are still being monitored.
So when the Fukushima earthquake happened in March 2011, what really happened was a few kilometers outside the Japan Sea, there was an extremely large earthquake where the 2 plates moved against each other. But what people didn't realize at that time as well was that there was a big cable cut. All the cables that were going into, most of the cables that are connecting Japan to US were cut during this earthquake. Recently,
a monstrous eruption which has left its mark on our planet. When Hunga Tonga Hunga Ha'apai blew its top in January, it scattered water vapor and ash halfway to space and sent tsunami waves swelling out across the world. A new survey offers a fresh picture of the scale of what happened. Scientists have fully mapped the area around the volcano, showing just how badly the seafloor has been sculpted and scarred.
We didn't map enough. This volcano even exceeded our maximum expectations about how far the effects of this eruption was on the sea floor. It really was an absolutely outstanding event.
The eruption produced one of the biggest atmospheric explosions in history, and the impression left on the seafloor gives a sense of its violent energy. Scientists calculate that some 10 cubic kilometers of material has been displaced, equivalent to the volume of 4,000 Egyptian pyramids. 2/3 of that was the ash and rock ejected out through the volcano's opening, but the other third was material scraped off the sides of the volcano as debris fell back out of the sky and tumbled across the bottom of the future. Tom.
So when this volcano erupted in Tonga, it took away the only cable that was connecting Tonga to the rest of the world. People had no idea how much damage has happened in Tonga and how many people have lost their lives. There was no way of providing any support to the country. Although the original fiber optic cable was not laid on top of the volcano, it was laid about 50 or 60 kilometers away from the volcano. What happened when the volcano erupted? The ash and the molten lava that it created, it almost made an avalanche under the sea and pretty much washed away the cable. About a 70-kilometer section of the cable was washed away. This happened
In March, countries along the coast of West Africa lost internet. Hospitals couldn't locate patients' records. Employers couldn't pay their employees. There were rumors of a coup. There were rumors that sabotage had taken place, and people had to go looking for answers. These cables run past Ivory Coast, and they also land there. The cables go through a canyon that begins near the coastline and then plunges seaward and gets deeper and deeper. The canyon is called Trou Sans Fond, which means the bottomless hole. On March 14th, an avalanche gets set loose in the bottomless hole.
So, underwater avalanches and landslides can happen as well. This doesn't only happen in the land or where snow is, it does happen under the sea as well. Again, that could put enormous amount of tension or push away some cables. So this is what happened in March 24 in West Africa. March, April, February in 2024 was a terrible time for fiber optic cables. It took over, many cables were destroyed in that time. And in South Africa, because of this cable cut, all the connections almost ground to a halt for 2 or 3 days.
So it remains unclear how the Houthis could attack subsea cables. The rebels are not known to have the diving or salvage capability to target the lines that sit hundreds of meters below the surface in the sea. However, subsea cables can be cut by anchors, including those dropped from ships disabled in attacks. A drifting ship with its anchor scraping the sea could be a culprit. Experts say 14 cables are now running through the Red Sea. The Houthis have warned that any cable-laying ship entering Yemeni waters needed a permit from the rebels.
So this damage happened again February 2024. The Houthi rebels mounted this ship and they sank that ship. When this ship was sinking, the ship actually dropped anchor, and that anchor was drifting at the bottom of the Red Sea. And it took over 3 cables, including SMIEEE 4, I think, that service Sri Lanka. So even in Sri Lanka, the cable speeds dropped. Again, last month or the month before, near Saudi Arabia, about another 3 cables have gone down. We still don't know the real answer for it, but there could be a huge amount of sabotage. And at the moment, there is, in the Baltic Sea, there is a huge amount of activity that's happening because of the Russian and the Ukrainian war that could cut or sabotage some of these cables. So not only humans, sharks, fishing nets, volcanoes, and earthquakes. All these events are a threat to subsea cables. So what are we going to do about it? And the subsequent thing is when earthquake or a volcano happens under the sea, it generates a tsunami wave. And that tsunami wave could be very devastating. As we know, in Sri Lanka in 2004, the day after Christmas, nearly over 30,000 people lost their lives because we didn't know what a tsunami was. And the tsunami actually happened near Indonesia, and it took 2 hours to get to Sri Lanka, and there wasn't any adequate warning system to protect our citizens. So what can we do about it? Let's start with the earthquakes and tsunamis. Normally, there are many earthquake has two parts. One is the seismic wave. A seismic wave we call a P wave and an S wave. They travel much faster than a tsunami. So what can we do? We can use earthquake monitoring systems that are already in place and provide some early warning system. And this is what's happening now in Sri Lanka. If you go to the coastal areas and if there is an earthquake in Indonesia or anywhere in the Indian Ocean, we do get an alarm and people are asked not to go to the sea. But the biggest problem we have with earthquake detectors is most of these earthquake detectors are land-based. And obviously, we don't have a lot of money to put lots of earthquake detectors. Normally, the current earthquake detectors are about 200 kilometers apart. And if we lose one sensor, if the signal is not picked up by a sensor, that means we lose 1 minute of warning time. So this is what happened when the Fukushima earthquake hit. These are the land-based sensors in the US. And you can see at the bottom when the S and the P wave has hit. And this is like a few seconds after the earthquake hit Japan. You can see all the land-based earthquake sensors lighting up, showing that it's detecting it. Yes, this is a very good way of helping people, but by that time, people in Japan would have already had the tsunami heading them there because it was closer to them. There are some earthquake sensors that are deployed under the sea, which are these dart-based buoys, which are floating. So there are sensors which are going all the way down to the sea floor. And then the signal, or if they picks up any disturbance, that information is fed through to a land-based system via a satellite or some communication system. So these are some of the sea-based buoys that have been placed around the world. But obviously, only the rich countries can afford to put this kind of service to protect themselves. So Japan has taken a lot of effort to protect their country because they are vulnerable from earthquakes. So here in this map, I map the sea and the land-based sensors around the world. On top of that, I am putting all the cables, subsea cables that are currently in the world. And then this is the map of all these dots on your cable are earthquakes that has happened in the past year or so. You can see there's a big correlation where at least an earthquake has happened on a subsea cable or close to a subsea cable. So there has been a lot of money invested from people like Google and Facebook to use subsea cables to detect earthquakes, not only detect earthquakes, also detect any sabotage, any ships coming closer, and provide early warning system. So one of the methods they have tried was to use new cables, and on the new cables, they put lots of new sensors like accelerometers, pressure gauges, temperature gauges, and this information is provided to the shore. And we monitor any changes of that. So we've been putting all these sensors to see any changes and provide an alert based on that, whether it's an intruder, an earthquake, or a tsunami. However, these repeaters have proved very costly. The Medusa cable in the Mediterranean was one of the first cables that should have had a smart optical cable with ability to detect earthquakes, but that has been pushed back because of the cost of these repeaters. The next thing that's happened is they've developed a new technique called distributed acoustic sensing. So where we could detect such as cable cuts or any tremors close to a fiber optic cable by using a dedicated fiber. So the black fibers are the ones that are taking communication. The yellow fiber is a dedicated fiber, which we use as a listening device. It's almost like putting a microphone on a cable. We take one of the fibers of an optical cable, and on that, we send a sound wave. And we look at what is reflected back on the sound wave. And even a minute disturbance or a change on that sound wave can be detected, providing us information about activity or closer or on the cable. Now, I can show you some of the examples in a minute. So this information is then processed by somebody, and using machine learning and AI, they can kind of figure out what kind of intruder, what kind of activity that happened on the cable and locate it. So this is the signal that generated the DAS cable system like almost to the cable. So that excavator going past a cable. This is an excavator that's leading close to a cable. And even a subtle thing is somebody actually walking along or close to the cable can be detected by DAS or digital acoustic sensing. So a lot of effort has been put onto this method to try and figure out what can be done. Now, this method has some limitations. There is a range limitation. So DAS is only effective to about 200 kilometers. So once you get from the coast 200 kilometers out, and after that, you don't get quite a significant signal back to detect any disturbances. So then there has been another method developed in 2021, which I was also part with Google on this activity, where we actually use the transmission signals, the actual data that is carrying your information from one place to another place. We look at various parameters inside that signal and see if there are any changes. Now, most of you might have gone to see 3D movies. 3D movies come to your eye in that format because one of your eyes, the two eyes have two different polarization states send information to your eyes. Light is electromagnetic wave. So that has a magnetic field and an electrical field. And these two fields are orthogonal to each other. What we can do is we can manipulate, or we can look at changes on the magnetic field or the electrical field and the differences between the two and figure out whether there has been a big change along the cable. So what we found is that by looking at those signals on the receiver on one side, we can actually detect any changes. So if there's an earthquake happening, there'll be a significant change on the signal level at the end. But unfortunately, this method means, yes, on a very long cable, let's say between Singapore and Sri Lanka, we can say there has been an earthquake, but we cannot tell where the earthquake happened because it is not accurate to provide that kind of information. So what have we been doing? What I've been doing with my colleagues at Nokia. Now we have a very lovely feature on these undersea amplifiers. The undersea amplifiers, in order to monitor their health, there is a little loop back. Part of the signal is extracted and sent back to the other side from each repeater. So, and it happens at a specific wavelength, that 1561 nanometer. 99% of the signal is passed through, but 1% is sent back to the transmitter on the other cable. So what we do is we use this particular feature to advantage. Now, rather than monitoring the health of the repeaters, we use that to monitor and detect if there's any tsunamis or earthquakes under the cable. So we send an optical pulse at this particular wavelength, and then we look at every pulse that is written by every single amplifier along the cable. Depending, since these amplifiers are like 50, 60 kilometers apart, we can actually detect or predict and locate an earthquake or any disturbance to within 2 repeaters. So which is about a 50, 60 kilometer range. In 2022, we came up with this particular design where we looked at the polarization of the light. We send a pulse into a repeater from Los Angeles on a cable that goes along the Pacific coast to Chile. And there were 110 repeaters, amplifiers on that link. And we were collecting the information for almost a year to look at earthquakes. So these are the different polarization elements of different signatures of the pulses, and each of these peaks is an amplifier or a repeater along the cable. So every 105 milliseconds, we would send a new pulse, and we collect 110 pulses from each of the repeaters. And we keep repeating this for almost a year. So if nothing's happening, let's just take the 90th repeater, for instance. These parameters look calm. There's no significant change on the signal. But on 22nd of February 2022, in Argentina, there was a powerful earthquake. And this, where the star is, and that signal traveled along the land, along the sea, and hit the nearest repeater. So this hit, I think, repeater 98 or something. That was the nearest repeater. And what we saw was the signal from repeater 98 would get a significant burst of changes. This work has been published since 2022, and this was able to detect and locate an earthquake to a nearest repeater on a cable. Now, after that, there was a big argument, guys, can you go and not only find earthquakes, but can you basically track a tsunami? If the earthquake creates a tsunami, can you check the tsunami? Now, this was a big bit of a problem because earthquakes are fast-moving things. In terms of fiber optic transmission rates, tsunamis are very slow, like a snail pace changing things. So the technique we used was not capable of detecting or tracking a tsunami or tracking an ocean wave going across the land or the ocean. So again, we went back on another cable between Portugal and Brazil this time. Rather than using a polarization analyzer, we started looking at the phase of the signal. So we looked at the phase changes of the return pulses, and what we changed was this particular unit here. Rather than from polarization, we use a phase detector on that location. Now with that, again, this is the cable from Portugal to Brazil, Fortaleza. Each of these peaks are return pulses from each of the amplifiers along the cable. From that, we were able to detect wave changes. So these are how the water currents or the surface waves move across the ocean. And we can track the movement using the pulses that we got. So now we have the ability to combine the polarization method with the phase method now to detect an earthquake and also to track the earthquake. Now, the same method can also be used to look at human activity, ship anchors, and provide some warning systems. So I'm going to conclude my webinar here. Optical communication cables are the lifeblood that connects you to data that you need to get to. But the amount of cables, the density of cables in certain parts of the world is very high. And those parts are also subject to earthquakes, landslides, volcanoes, and more problematically, human activities such as fishing, shipwrecks, sabotage. We have been trying to provide some kind of a sensing method to deter any human activity and also provide some sensing to people to save their lives in the event of a tsunami or an earthquake. There have been several methods that have been developed, like smart cables, DAS, and the method that I have presented to you. But where I need help from you is that companies like Nokia can have the money to develop these new techniques. But to validate the importance or the validity of those techniques, we need support from academics. As Nokia is a data communication company, we don't have access to the geographical data, the seismic data. We also do not have the time to correlate the seismic data with the data that we collect on these cables. And we also need people to develop machine learning and artificial intelligence algorithms to not only correlate these things, but provide some early warning systems. So the work in sensing threats to cables are at this point where we need partnerships with academic institutes and new students where we can share the data and improve detection methods and provide a service to mankind. Thank you very much.
Thank you, Professor Sumudu, for this insightful session. So now we would like to open up the floor for the question and answering. And also we have one question directed, Professor.
Okay.
This, who will invest for the cables and who will be responsible for paying for the repairs and maintenance cost?
So investment of the cables, for instance, SMIEEE 5 and SMIEEE 6. Sri Lanka Telecom is part of the consortium. So Sri Lanka Telecom invests as a contributor to that consortium and pays for the laying of the cables and also for the repairs. Similarly, Dialog Sri Lanka also own parts of subsea cables like AAG, IET, few cables that go through Sri Lanka. So normally it's a very powerful company like Sri Lanka Telecom working in a partnership with a group of companies. So SMIEEE 5 or SMIEEE 6 has Telecom Egypt, Singapore, Telecom, Singtel, few other companies who are providing money and support to that. But also there are private cables which are owned by Google and Meta or Facebook or Microsoft. They have their own cables. So they have the money to invest and protect and say, look at their cables. What I found with the activity that I'm doing, developing techniques for earthquake detection, it is those companies, private companies such as Google and Meta who provides the money. But then once we develop something, everybody else, like the consortiums, would try to use that technology to help them. What's the next question?
There's another question, Professor. It's quite long, so is it possible for you to go to the chat?
Yeah, let me look in the chat. Paul. So 1 second. I'm just going to ignore that. Plenty, but underwater much more harder. Even COTDM pinpoint how do operators. Um, so Jairam, two methods. Um, Subsea cables are powered by electrical PFEs on each side. And these electrical PFEs normally share the power load on each side. When a cable gets cut, that point that gets cut gets grounded, and that goes to zero voltage. So that provides an offset in the power feed, the voltages. Using that, you can kind of figure out where the cable break is. Otherwise, you need things like COTDR or even this technique that I'm talking about in order to locate earthquakes. You can use that to locate the cable break position. How do you reduce the cost of repairs? Obviously, just like a doctor, prevention is better than cure. So don't wait until cables are broken. One, try to plan ahead so that you put the cables in a better location. In Mount Lavinia, if you go to the SMIEEE site, they have lots of sensors looking and radars looking at the ship movements. They have connectivity with the Coast Guard to prevent any fishing or shipping lines coming close to the our fiber optic cables. So that's one. Is there any possibility of utilizing fiber brag gratings? Yes. Submarine networks do use some of the fiber brag gratings, but that's an interesting point. We are looking at using fiber brag gratings inland as well as under the sea to look at improve the sensing capabilities. So Nipuna De Silva, I think you can send me an email. I will put my, I will ask Achini or Nuan to share my email address. So we can, I will share with you my mobile number so you can contact me through WhatsApp. Danushka has a, how can we trace a cable breakdown in live network using OTDR? Yes, you can. You cannot use, if there's a breakdown, then the cable is no longer live, right? If there's a breakdown, there's no traffic going through, you can use OTDR. But most of the new cables are built with in-service OTDR function, just like the special wavelength we use for the subsea cables. You can use a special wavelength that is not used for communications. So in land cables as well as subsea cables, we continually monitor the cable health with the live traffic going through it with that technique. Can electricity be carried in a subsea cable? Yes. There are many electrical subsea cables, and electricity is required for optical cable to provide amplification. So the amplifiers need electricity to generate optical amplification. What will be future undersea capabilities because of Starlink? Starlink is not a threat because a fiber optic cable, a single fiber optic cable, can carry something like 20 terabits of data at a given point, depending on the distance, of course. But if you look at the Starlink, even the link itself can only manage maybe a gigabit of data. So fiber optic cables will always be much, much bigger and have a bigger capability of carrying data. So Starlink, yes, is a good thing, but it's not for the long distance and the bulk communication. Can you explain, so Danushka, about optical amplifiers? This is not something that I can do on this lecture. We can schedule another lecture if you are interested, and I can go through a lot more details about fiber optic subsea cables. So there's more, yeah, exact information. What else? Is there an alternative for Sri Lanka? If a subsea cable get damaged, how many days will it take to recover? So normally when Sri Lanka Telecom or Dialog build subsea cables, they don't just build one cable like in Tonga situation. Sri Lanka has more than 6 or 7 cables that come in. For some reason, if one cable goes down or one cable gets broken, we can divert the traffic to another cable. But that means, you have to pay money to have a reservation. You need to have allocation of that extra capacity. I may have a proposal. Yeah, if you have proposals, I am always looking for new research students to do work for me. I already have one from one of my PhD students from SLTC working at the University of Jawatanapura on a sensing-based PhD. So I'm always happy to help you. I'm happy to write papers with you or provide ideas. So thank you very much. I'm happy to work with you. Any other questions, please provide that back to me, or I will read this chat later, or Achini or Nuwan can email them to me and I will reply to you. Please share my email address, and those who really need my WhatsApp number, I will share it through email. And Jerem, nice to see you again on here, and I hope you're doing very well, and best of luck to you. Any other questions? I have a flight to catch in about 1 hour.
Okay, sir. One last question. I see this who is responsible to provide physical security out at sea for these cables?
So there are new companies that are being formed who are looking at sensing. Some of them are security companies, which are like Avantgarde, which we had to provide security in certain parts of the world. So all these are happening as we speak because these are new threats we didn't expect. But ultimately, the cost will be borne by the people who own the cable. So that will be your Sri Lanka Telecoms or your Googles or Meta or Singtels and Bharti, Airtel and so on. Whoever owns the cables will have to ultimately bear the cost.
Thank you, Professor. So we will wind up this Q&A session, and for the contact, we will share the professor's email with the attendees today. So you can contact Professor and get your questions clarified. So once again, I would like to thank our Professor Sumudu Edirisinghe for this fruitful session. Undoubtedly, it helped our students a lot. And I would like to thank our audience who joined. And we would like to wind up this session. And thank you very much for joining, and good night.
Thank you very much. Good luck to all of you.